This is the lesson for section 9.7, which is the last section we will be covering in chapter 9. And for this lesson, we will be solving logarithmic equations. First thing we have to do when solving logarithmic equations is to remember what the domain is for logarithmic equations. So one thing that we've said is that for logarithms, we usually only talk about the base being greater than 0 and not equal to 1, because we can't talk about raising negative numbers to powers. Likewise, we can't plug negative numbers into a logarithm because, again, we end up with that issue of negative numbers raised to a power and oscillation. So in this case, the one thing that we need to recall is that given f of x is equal to log base b of x, then the domain of this function is x is greater than 0. And again, we cannot plug 0 in for this. So let's look at our first example. First thing we need to do is find the domain of the equation, and then we will talk about how to solve it. So if we want to look at the domain, we need to make sure that both 2x plus 1 and 4x minus 5 are always greater than 0. So we're going to solve both of these inequalities, and then whichever one is less inclusive we will consider to be our domain. So in this case, if we've got 2x plus 1, we need that whole value. So when we say x here, we mean that whole value. So in this case, it would be 2x plus 1 needs to be greater than 0. We subtract the 1 over, we get 2x has to be greater than negative 1. And then we divide by 2 to get x must be greater than negative 1/2. So that's one element. Let's see what the other one produces. We have 4x minus 5 is greater than 0. We add the 5 to the other side, so 4x has to be greater than 5. And then we divide by 4 and we get that x has to be greater than 4/5. So if you look at these two things, and if you want to kind of put things on your number line here just to make sure, we'll put 0 here, we have negative 1/2, and we have 4/5. So for the negative 1/2, we say we have to be greater than that value, and for 4/5 we have to be greater than that value. So in this case, the 4/5 is actually more restrictive. It's leaving off some of the values we could plug into log of 2x plus 1, but at least it's not making the other function undefined. So in this case, our domain is just restricted to the more restrictive one. The domain in this case is x is greater than 4/5. And again, if you want to write this in interval notation, this would be from 4/5 with a parentheses because we're not including the point up to infinity. So there's the first part of our question. The second part is to solve these. And now if you remember, logarithms and exponential functions are inverses to each other, so to get rid of the other, we can use the base power of whatever our logarithm is and raise both sides to this power, or make both of these the same base, which was whatever the logarithm base is, and then raise that to make both of these sides the exponents. So another option that you can go with is combining things using our properties of logarithms, and then again rewriting it in exponential form. So in this case, we can look at this and say, okay, these are both log base 10, so we can make 10 our base and our exponent this entire thing. So then the 10 and log and 10 to the log is going to, in essence, cancel because these are inverse operations. They're going to get rid of each other, and we're just going to simply be left with 2x plus 1 is equal to 4x minus 5. Now it's just a matter of simple algebra. Also, we can think about this if we have two logarithms that are of the same base. we can simply just set their internal functions equal. So in this case, we have 2x plus 1 is equal to 4x minus 5. So to solve this, I'm going to subtract the 2x from both sides to get the x's by themselves, and I'm going to add the 5 to both sides to get them by themselves. And then in this case, we are left with 6 is equal to 2x, so x would be 3 in this case. That does fit in our domain that was given as being greater than 4/5, so we are okay in this case. This is our solution to the function. I'm going to start off the next example for you, and then I want you to continue solving it. So in this case, we have the natural log of 5x minus 100 is equal to the natural log of x. I want you to go through and find the domain of the function, but I'll give you a hint again. Anytime you have a log with the same base and they're set equal to each other, we can just take the inside function and set them equal, or we can get rid of the natural log function by making e the base and raising both of these functions as the exponents. So take a second here, pause the video, and then resume to see if you've got the correct answer. So you should have found that your domain is that x is greater than 20. That's the more restrictive of the two, and that when you solve the equation, you end up with x being equal to 25, which is greater than 20, so we're good in this case. Now we need to talk about what happens if either you have a coefficient on one of the terms or you have multiple logarithm terms on one side. And in those cases, we just use the properties of logarithms. So for instance, when we see 3 natural log of x here, then we are just raising that up as we're making that into our exponent here. So this becomes the natural log of x cubed is equal to the natural log of 8. Again, we want to make sure we find our domain first. So x cubed has to be greater than 0, which means that x has to be greater than 0. So that's our domain in this case. Again, if you want to write it in interval notation, that is our domain. And now if we want to solve this, again, we've got natural log equals natural log, so we can say that x cubed is equal to 8. Again, we could raise both sides, make e our base and raise both sides as the exponents. We would get the same thing. So in this case, x cubed is equal to 8. We can take the cube root of both sides to find our other real root. And we are left with x is equal to 2 in this case. And that is greater than 0, so it fits within our domain. Continuing while talking about the properties of logarithms, in this case we've got 2 logarithms on the left-hand side, so we want to combine these together into one logarithm. So in this case, we use our properties of logarithm. Remember, subtraction outside means division inside. So we get the logarithm of 2x plus 1 over x minus 4. And that is equal to the log of 3. So in this case, to make sure that we end up with a proper domain, we are going to look at when is 2x plus 1 greater than 0. And in this case, we also need to make sure, in this case, x does not equal 4 because that would make the denominator 0. We also have to worry about what is going to make the denominator negative. So in this case, we have 2x plus 1 is greater than 0. For the first part, we subtract the 1 to the other side. We get 2x is greater than negative 1. We divide by that half, and we get that x is greater than negative 1/2. For the x minus 4, we already said it can't equal 4 because that'll make the denominator 0. But on top of that, we have to be even more restrictive. We have to make sure that it's positive. So x minus 4 has to be greater than 0, meaning that x has to actually be greater than 4, not just not equal to, because then that will make the denominator negative. Something to keep in mind with this example, though, since we have these two combined, if you think about if the numerator is negative and the denominator is negative, then the negative divided by the negative would give you a positive answer. And so in that case, x is greater than 4 is going to be part of the domain, but actually x is less than negative 1/2 would make the 2x plus 1 negative and the x minus 4 negative, and so again you'd have that negative divided by a negative, which would give you a positive. So if we kind of reverse this here, we end up with a combined domain, which is x is less than negative 1/2, x is greater than 4. So in this case, if you wanted to write this in interval notation, you'd have to union these two together, and it would be from negative infinity to negative 1/2 unioned with 4 to infinity. So this is the entire domain in interval notation. Again, and that first set is because you would have a negative divided by a negative, and the second half is when both are positive. So to continue with this problem, I'm going to move it over here so we have a little bit more room to solve if we need it. We end up with, so we both have log base 10. We can either just set these two equal, or remember that to get rid of the logarithm, we have the anti-logarithm. And so we end up with 2x plus 1 over x minus 4 is equal to 3. So again, if you remember your algebra, you want to get rid of this denominator, so you're going to multiply both sides by x minus 4, and we make sure to put our parentheses so we distribute to the 3. So now these are going to be divide to be 1, and we have 2x plus 1 is equal to 3x minus 12. So in this case, I'm going to subtract 2x and add 12 to move things to the other side, and we are left with 13 is equal to x. So if we check to make sure that that is in our domain, it is greater than 4, so we are okay. X is equal to 13 is our solution to this problem. Sometimes we end up with logarithmic equations that do not involve logarithms on both sides, and again, this is where we need to remember which base it is to get rid of the logarithm. So again, first things first, let's find the domain. Let's rewrite this function, bring the 2 up as an exponent, so we have the natural log of x squared is equal to 1. To find our domain, we say that x squared has to be greater than 0. So in this case, x has to be greater than 0. So there's our domain. And now if we solve this equation, again, we need to use e in this case. So we're going to have e, and then both sides are going to become our exponents. So the e and natural log are going to get rid of each other. And we're going to be left with x squared equals e to the first, and anything to the first power is just itself. Again, remember that e is just a number. So now to get rid of the square, we were going to take the positive and negative square root of e, which gives us that x is equal to plus or minus the square root of e. Now we need to come back to our domain. Our domain says that we have to have only positive values, so we don't need this negative. The negative is not going to be an issue. So in this case, because our domain is restricted, x is only equal to the positive square root of e. And if you wanted to, you could find the decimal approximation for this, but you don't have to. Again, remember, e is just a number. So I want you to try example 65 now. So in this case, you should have gotten that your domain was x is greater than 1, or from 1 to infinity. And if you go through and solve this one, you end up with x should equal e squared plus 1. Again, you can find the decimal approximation for this, but you really don't have to. And in this case, you know that this is greater than 1 because you've got 1 plus some positive number. E is 2.7, and you're squaring it, so it's going to be larger than that. And if you're adding 1 to it, then it is definitely going to be greater than 1. A few more examples here, and these, again, just rely on the properties of logarithms to do some simplification ahead of time and then go through and solve. So for example 66, we're going to again use our properties of logarithms. The 3 outside is going to come up as our exponent on the 3 inside. So If we rewrite this, we have the log 2x plus 1, and then we are multiplying because we've got addition, 3 cubed, and this is equal to 3. So in this case, to find the domain, the 3 cubed isn't going to affect our domain, but the 2x plus 1 will. We've done this one a few times. We subtract the 1 over. We have 2x is greater than negative 1. X is greater than negative 1/2. So again, our domain is restricted to negative 1/2 to infinity. Now to actually solve the problem, and we are going to say that we need to get rid of the common logarithm, which is log base 10. So we are going to have 10 as our base and both sides as our exponents. So again, we're going to end up with 2x plus 1, and then we've got this, 27, because that would be 3 cubed, is equal to 3. So again, it's up to you how you want to proceed as far as your algebra goes. You could divide by 27, but that's going to create a fraction off the bat. So let's instead distribute the 27. So 27 times 2 is 54x, plus 1 times 27 is 27, and this is equal to 3. I'm going to subtract that 27 over, and we're going to end up with 54x is equal to negative 24. Divide both sides, and you end up with x is equal to negative 24 over 54, and yes, this does reduce to negative 12 over 27. You'd end up with a common denominator of 54, which would make this negative 27 54ths, and negative 27 54ths is left of negative 24 54ths. So in this case, we're okay. Or you can go to your calculator and you can say negative 12 divided by 27, and you can find that that's negative 0.444, which is again negative 0.5 is to the left of negative 0.44. So this is in fact greater than our required value to fit in our domain. I want you to pause the video here and try example 67. So for this example, you should have found that your domain was x is greater than 1/2, and when you go through and solve everything, you end up with x is equal to e plus 2 over 4, which is approximately equal to 1.18, which is greater than 1/2. The other way you could determine if this is greater than 1/2 is that e is 2.7. If you add 2 to it, you end up with approximately 4.7. 4.7 divided by 4 is going to be greater than 1. So we know that we're definitely going to be greater than 1/2. A few more examples here. In this case, this one's a little bit more involved because we need to worry about putting all the logarithms on one side and the non-logarithms on the other. Again, for our domain, just to make sure that we are in the correct place, we have x has to be greater than 0 in this case, and for our other function, we need 2x minus e has to be greater than 0, so 2x has to be greater than e, and x has to be greater than e over 2. So again, this is a positive number.
So the first thing that we need to do here is we need to rewrite this equation so that all of the logarithms are on the same side. So we're going to move the natural log of 3 over to the left and the 2 over to the right. So we end up with the natural log of x plus the natural log of 2x minus e minus the natural log of 3 when we subtract that over, and then we're going to add that 2 over, and we'll get just positive 2 on the other side. Now we can use the properties of logarithms to combine these three logarithms here on the left-hand side. So we end up with the natural log of x times the quantity 2x minus e, and then this negative means we're going to be dividing by 3, is equal to 2. Again, to get rid of the natural log, we need to raise both sides with e as the base. So e and natural log are inverses. We end up with x times 2x minus e over 3 is equal to e squared over here on the right side. Now we're just solving for x here. We can multiply that 3 over. We can distribute that x there. So if we come over here, we end up with 2x squared minus ex, and again, this is not e to the x, this is e times x, e is a coefficient in this case, is equal to 3e squared. And we can move the 3e squared to the other side. In this case, it looks like we're going to have to use the quadratic formula, which isn't real pretty. So we end up with 2x squared minus ex minus 3e squared is equal to 0. Again, a is going to be 2 here, negative e is going to be our b, and negative 3e squared is going to be our c. So we end up with x is equal to negative e plus or minus the square root of negative e squared minus 4. A is 2, c is negative 3e squared. All divided by 2 times 2. So when we simplify here, we end up with positive e plus or minus the square root of e squared. Negative and negative is going to give us a positive. We got 4 times 2 is 8 times 3 is 24 e squared over 4. And that can get simplified since those are both e squared. We can end up with e plus or minus the square root of 25e squared over 4. And since 25 is a perfect square and e squared is a perfect square, we can end up with e plus or minus 5e over 4. So if we add e plus 5e, we end up with 6e over 4, which reduces to 3e over 2, or 3 halves e, which is within our domain x is greater than e over 2. And if we subtract, we end up with negative 4e over e, which is negative, so that is not within our domain. So our only answer here ends up being our 3e over 2. Now I want you to pause the video here and try the next example. So for this next example, you should have found that your domain was x is greater than 2, because that x is greater than 0 is encompassed in that. Grouping the terms on the left side with the laws of logarithms, you should have ended up with the natural log of x times the quantity x minus 2, and getting rid of those natural logs by using e, we end up with this nice quadratic equation. We can set it equal to 0, and it factors into x minus 3, x plus 1, and that would give us the answers of x equals 3 and x equals negative 1. Now negative 1 is an issue here because it's negative and we need a number greater than 2, so we are simply left with x equals 3.
Got 2 more examples here. The first one here is very similar to what we've done before, so I want you to pause the video and get one last practice here before we move on to the application. So for this example, when you rewrite the function as x minus 1 quantity squared, remember that when you square anything, it's going to make it positive. So no matter what you plug in here, it's either going to be 0 or positive. The only thing we have to worry about is we still can't plug in 0. So in this case, our domain is only restricted to be x is not equal to 1. So if we go through and work this out, you should get x squared minus 2x minus 9 equals 0. And for that, you need the quadratic equation, and you end up with these 2 decimal approximations, or the exact answer of 1 plus or minus the square root of 10, all divided by 2.
The examples that we've looked at thus far in the chapter have dealt with the natural log and the common logarithm. This example, however, is going to deal with a log base 7. Again, to find the domain, we would go about the same process. So we would look at our first term. We would say, okay, well, x has to be greater than 0. And then we look at our second logarithm there, and we know that 2x minus 5 has to be greater than 0. Move that 5 over, 2x has to be greater than 5, and x has to be greater than 5 halves. So this is all-encompassing. It includes that x is greater than 0. So we'll just stick with that as far as our domain goes. Now solving this, we're going to go about the same process to start off with. We are going to combine our logarithms, so we end up with log base 7 of x times 2x minus 5 is equal to 2. The only difference here is that instead of this being log base 10 or log base e, it's log base 7. So instead of using 10 or e, we are going to use 7 as our base and both sides here as our exponents to get rid of that log base 7. So over here we're going to end up with x times 2x minus 5, and over here we end up with 7 squared, which is 49. So distribute that x, move the 49 over, we get 2x squared minus 5x minus 49 equals 0. You can try to factor this, but it doesn't work out real nicely. So we're going to go to the quadratic formula, and we end up with x is equal to negative 5 plus or minus the square root of negative 5 squared minus 4. A is 2. C is negative 49 all over 2, and A again is 2. So we do some simplification here. We got negative 5, which gives us positive 5, plus or minus. When you simplify everything in here, you get 25. You get 4 times 2 is 8. Times 49 is 392. So 392 and 25 gives you 417. And it's all divided by 4. Now this isn't going to simplify any further, so these are our two answers. We need to make sure that they are both bigger than 5 halves. If you wanted to, your 5 plus the square root of 417 is going to give you approximately 6.355, and your negative is going to give you approximately negative 3.855. So in this case, again, the negative is not going to work for us because we need our number to be greater than 5 halves, but this 6.355 will produce a correct answer.
For our final example, we are going to look at an application, which is the Richter scale, which measures earthquakes, the magnitude of an earthquake. The Richter scale compares the earthquake to a zero-level earthquake whose seismographic reading measures 0.001 millimeters at a distance of 100 kilometers from the epicenter where the earthquake started. This is represented by the following function, where x is the seismic reading. And there should be a negative here. In this case, the magnitude of an earthquake is equal to log of the fraction x divided by 10 to the negative third. So, in this case, San Francisco, California experienced its largest earthquake in 1906. Its seismographic reading was 7,943 millimeters at 100 kilometers from the epicenter. So again, this is our x, this is our seismographic reading. So we can plug this in. M is equal to, in this case it would be log of 7,943 divided by 10 to the negative third. And in this case, we can simplify this. So this would just be log of 7,943, and then we can add 3 zeros here on the end. So if we take log of, and we can plug it in either stage. You can either plug it in the first step as 7,943 divided by 10 to the negative third, and you end up with 6.89. Or you can take log of 7,943,000, and you end up with the same thing. So in this case, the magnitude of this earthquake was approximately 6.9, which is very high. It's the largest earthquake in San Francisco. Now, recently, we had a small earthquake of magnitude 4 in Youngstown, Ohio. What was the seismographic reading 100 kilometers from the epicenter? So in this case, we know that our M is 4. So 4 is equal to the log of x is what we're looking for, divided by 10 to the negative third. In this case, we're going to need to do a little bit more work. We're going to have to get rid of that log, so we're going to have 10 as our exponent on both sides. We have 10 to the fourth is equal to x over 10 to the negative third. So now to get rid of that, we would multiply by 10 to the negative third on both sides. And in this case, 10 to the negative third times 10 to the fourth, add those exponents, you end up with 10 to the 1 is equal to x. So in this case, x was simply just 10 millimeters. Not a whole lot. And if you didn't feel it, I don't blame you. So this concludes the video for 9.7. Go online now and complete the homework for this section and then the quiz for the rest of Chapter 9.